Hello and welcome to Talking Papers, the podcast where we talk about papers and the papers do the talking. And today we're going to be talking about UCNet, uncertainty-inspired RGB-D saliency detection via conditional variational autoencoder. And the author that I have with me today is Jing Zhang. Hello, Jing.
Hello, Isaac.
This is a CVPR 2020 Best Paper nominee. And Jing, introduce yourself.
Hi, everyone. This is Jing. I'm a PhD student in Australian National University. And this is the third year. And I think I'm going to finish my PhD in the coming 2 or 3 months.
Yeah, so about the authors, who are the collaborators here?
So the authors in my paper include me and also Deng-Ping from Nankai University, Yuchao from Northwestern Polytechnic University, Fatemeh, Saeed, and Tong from Australian National University, and also my supervisor Nick from NAU.
Let's dive into the abstract. So in a TLDR, 2-3 short sentences. What is this paper about?
So firstly, it's about silent object detection, which aim to segment the silent objects in a given scenario. And in this paper, we want to deal with uncertainty estimation, which means instead of produce the prediction as well, we want to estimate the uncertainty of prediction.
Yeah, that's a super interesting thing. So if we boil it down to inputs and outputs. So your input is an RGB-D, right? An RGB-D image, and your output is basically your saliency map, right? This kind of a mask segmentation of what is salient in the image.
Yeah. But instead of a single prediction, because typically for saliency detection is a 1-to-1 mapping, you have the RGB or RGB-D image pair, and the output is a single saliency map. But we want to estimate a series of predictions because this is more consistent with our vision system. Because when you see a scenario, usually different people can have different definition of saliency. So yeah, that's what we want to do and what we think is more interesting about saliency.
Right. So your output is not a single saliency map. It's like multiple ones. It ties into the fact that if you show a person the image, one person can say, oh, this is the salient part. And another person would say, no. The salient part is the thing here at the back, actually. Moving on to the introduction. What problem is this paper addressing?
Yeah, the first time when I noticed there's a problem about saliency is when I just go through all the data set. Because for saliency detection, we have a lot of data sets, like 7 or 8 testing data sets and 3 training data sets. When I just go through this data set, I observe that actually subjective happens, which means sometimes the ground truth is different from my definition of saliency. And this is the time when I realize that saliency should not be done in a one-to-one mapping way. There must be something different, something subjective behind saliency detection. That's why we want to produce a model that can produce a series of predictions instead of a single prediction. And this is simply our motivation.
Let's go back a little. Why is it an important problem? Why do we need saliency at all?
Okay, for saliency usually can provide you a prior about the main focus of a scenario, and also saliency because it's class agnostic. You don't know the class of the silent object, but if you can produce a dominant area of the provided scenario, which can provide you the main information about scenario. Let's give you an example. Let's say I give you an image, I show you the image, and if you can produce a saliency map, usually the saliency map captures the main focus of this image, and with the main focus of image, you can get the main information of this image. So this is how people can define saliency, and you can use saliency to do like image compression because you don't want to lose the information in the silent area. You can just compress the information in the non-silent area, and also because it's class agnostic, the output of a saliency map can be its generation ability of saliency model usually is better than some semantic segmentation model because usually for semantic segmentation you have predefined categories. And if you train on, let's say, for Pascal or for Cityscape, you train on this data set, and when you test on a scenario which have no categories including the Pascal data set, your prediction gonna be not very good. But for sense detection, it's class agnostic. You can always use it in a real world scenario.
What are the main challenges in this field?
The main challenge may be overfitting, to be honest, because usually the model trained on dataset A, usually the training dataset control we have is 3 training dataset. It's quite simple. If we train on this very simple dataset, the generation ability, although it's not that bad because class agnostic, but still when you train on simple dataset and then you test on real world scenarios, the prediction sometimes not that accurate. And also one main issue of this one is model can be overconfident, which means when they make mistake, it's a huge mistake. It's not a minor one, and the model didn't even know or didn't even aware of the mistakes. So this is the existing problem of the current sensitivity detection models. But what we want to do is an uncertainty estimation model, which means we want to produce the prediction. At the same time, we want the model to know that in which area, please be not that confident because you are making a mistake. So this is our goal for this work.
This really builds up to the contribution of this paper. Yes. So what's the main contribution of the paper?
Yeah, that's the main contribution because, as I mentioned before, usually you produce one single prediction and you're not aware of your predictions. But with our model, because you have a series of predictions, it's a lot of predictions. Whenever you sample from the a latent space, the feature space, and you can have one prediction. So you sample several times, you can have several predictions. And with these several predictions, you can have the uncertainty map, which highlight the uncertainty area of predictions. And this uncertainty area just show that in this area, it's not good. The prediction is not right. Just be aware that it's not right. So this is the I think the most different part of our work compared with the existing work.
Mm-hmm. Yeah, so basically, instead of producing only one output, you produce multiple ones with kind of certainty. Okay, so moving on to the related work section of the paper. So consider that we have some novice listeners before they start reading your paper. Which one or two papers would you recommend reading?
Okay, firstly, because our technique is conditional variational autoencoder, so the original CVE paper should be the first priority, and the name is Learning Structure Output. The whole title forgot, but the initial one is Learning the Structured Output for Feature Representation. This is the title of the paper. So this is basically the first conditional variation autoencoder paper. Another paper I think quite interesting. The name is Probabilistic UCNet for medical image segmentation. And this actually my current work, this work is so inspired by the probabilistic UCNet for medical image segmentation, because although uncertainty estimation is not quite popular in especially for my task, but for medical image segmentation, uncertainty estimation is like very widely used. So in the medical image segmentation community, uncertainty estimation have been used a lot. There are a lot of papers using uncertainty estimation. And the probabilistic UCNet, this paper is quite typical, and their work use CVE for medical image segmentation. So I can say that my work of uncertainty estimation for sensitivity detection is quite inspired by the probabilistic UCNet for medical image segmentation.
Yeah, that's really nice. A paper that works on medical data was used here or inspired this work. This is amazing. I think like how can papers that you think have nothing to do with each other were actually really inspired. And yeah, and the uncertainty aspect of it, right? In medical imaging, that's one of the things that you want to have, right? Because you don't have a lot of data or it's imbalanced or whatever and you want to have a notion of uncertainty, right? You want to know how the algorithm is sure of its prediction. What is the key idea and innovation of this paper?
Okay, so typically this is a CVE framework. So for conditional variational autoencoder, you have two different encoders First one is the prior net, and also have a posterior net. And in our network, the uncertainty is try to model the labeling variance, which means the ground truth should be different. There should be several ground truths in our silence estimation task. But currently, the ground truth is one single version, which means the current ground truth for silent object detection is only one single version. But how can we generate a multiple version of ground truth with our data set? So we introduced the hide and seek technique, which had been previously used for image augmentation.
Hide and seek, kind of like my kids.
Yes, exactly. So we use hide and seek technique for our task to generate multiple ground truth silent map for our currently prevailing neural network. This is I think this kind of different from the previous way of using hide and seek technique. So with the multiple ground truth silent map, we can define the difference of the ground truth as a labeling variance, and to label or to model the labeling variance, we use a latent variable, and this latent variable is actually depending on the multiple ground truth. So we define the posterior distribution of the label areas as PZ give X and Y. X is the input image pair, Y is the ground truth, it's a series of ground truths. Mm-hmm. So with this posterior distribution, and also we have prior distribution, which means without seeing the ground truth, you should know that this image might have different definition of silencing. So this is the prior of Z, which is given by PZ of given X. So with prior distribution of the latent variable and posterior distribution of the latent variable, we just simply define their similarity as KR diversity. This is a typical way of using CVE. And also because it's a silencing detection network, you have a reconstruction loss, which is our, given our prediction and our provided ground truth, we want them to be similar. So simply we can use a cross entropy. So together with the distribution similarity and also the reconstruction error, we come up with our final loss function, which is the reconstruction loss as well as the distribution similarity loss, the characteristic loss.
Let me stop you for a minute. I want to pause and talk a little bit about the hide and seek thing. So basically what you're saying in the hide and seek, you're saying, well, the data sets don't have the data that I need, right? They only have a single saliency map. And we know that's a problem, right? Because there's more than one salient object in some of the images, not in all of them. So I have the question. You hide the salient object,
foreground.
The foreground, yeah. You hide the salient foreground, and you then run some algorithm to produce something else that's the foreground. So this, I have two questions spanning from it. One, what happens if there's no other salient regions, right? Like you may have something that's, I don't know, like a horse in a meadow, so the meadow is just background.
It happens a lot because usually when you prepare the ground truth silencing map, they do majority voting. They may have different labelers. Sometimes they have 5 labelers to label each image, and then each image end up with 5 different versions of silencing ground truth. So the final ground truth is obtained by doing majority voting. So which means the silent object in the current ground truth silence map is the most silent object. But for some silent objects, which is not consistently for those 5 or several different labelers, they're gonna be deleted or they're gonna be defined as background. So our hide and seek technique is trying to recover the deleted, not that silent objects or less silent objects, but it happens that for one image, these 5 different labelers have consistent definition of silencing. In each way, there's no area have been deleted during the majority voting. So it happens. So in our strategy, after several times of hide and seek, if we can't see the recovered area, we can define the silent ground truth as one single version of ground truth. So it happens for one image, maybe we will have 5 different ground truths, or for some other image, maybe we have only one ground truth. It happens. So it's simply based on the input image, whether it's complex or it's very easy.
And the second question that I had in this context is, when you hide the object, how do you prevent the, I guess you're putting just a black square on it. How do you prevent the algorithm from just detecting the black square as foreground?
Currently, we just not put it as black. We put it as the media value of the training data set. So this is a typical way used in heuristic technique, and it can prove, because usually if our backbone is from by using RASNet 50 or by using VG16, and usually you have to do data normalization, and do data normalization you have to subtract the mean value. So by assigning the area or the previous area with the mean value of the training data set, you can just ignore this area from contribute for Saliency detection.
Yeah, it's kind of like you're putting a part of the background, like the average background of the data set kind of thing.
Exactly.
Back to the pipeline. So we had our prior net and posterior net, right? One of them gets the input only, and one gets the input and the desired output. And you try to make them do the same thing, right?
Similar.
You try to make the distribution be similar.
Yes.
And then what?
After you train the model, the posterior distribution and the prior distribution should be similar. In this way, the latent variable they have already encoded the labeling variance, which means the latent variable now know that given this image, they should produce a series of different predictions, or it should produce a single prediction. Because if the image is very simple, as I just mentioned before, if the image is very simple, the foreground is quite obvious, and then the prediction should be consistent because there's no ambiguity about saliency for this scenario. But if the image is quite complex and there maybe exists some different definition of saliency, then this latent variable Z should be aware of this because he have already learned this stuff from the ground truth, the posterior net. So during test, given the image, we just use the prior-net to generate a series of features, because whenever you sample from the prior distribution PZ of X, you have this latent variable can control the prediction for this image. This is a way we use latent variable during test.
Okay, so during test, you're generating several samples, and you have like this new, like several predictions for the saliency. You also have a deterministic part of it.
You have deterministic part of this model because this part only generates the stochastic feature, and this stochastic feature wants to estimate the variance of ground truth or the uncertainty part of the ground truth, but there's still a deterministic part. This deterministic part try to get the saliency feature, because as we know, actually saliency, although it's subjective, but there should be some consistent definition of saliency for people. All different people should have some consistent definition. So it's like saliency is based on the consistent awareness of this task, as well as some ambiguity of this task. So the deterministic part try to capture this deterministic part of saliency, and the latent variable part, or the encoder, or what we define as the latent part. The latent part can capture the uncertainty part of the prediction. So we combine the uncertain part of the prediction as well as the deterministic part of the prediction to get our final prediction.
So you have the deterministic part, you have the stochastic part. How do you combine between them?
A concatenation is very easy.
And then feed that into
Saliency decoder. And this decoder, it's very simple, several convolution layers.
Okay, so again, you take the deterministic part, the stochastic part, you concatenate them, and you feed them into a decoder, and the output of that decoder is your final prediction saliency map.
Yes.
Okay, now let's talk a little bit about the results. So to those that don't know the world of saliency detection, what experiments are usually done and what metrics are used?
The metric, the most important metric is MAE, mean absolute error. So it's very simple. They simply compute the L1 error, L1 of the prediction and the ground truth, and it computes the pixel-wise accuracy of the prediction. This is widely used metric, although there are some other metrics like S-Merrow, E-Merrow, F-Merrow. But for me, I really trust the MAE because it's a per pixel-wise accuracy.
Okay, so you take the ground truth, you take the prediction. They should be as close as possible. Though like I have some reservation about this metric. What about the boundaries, right? The boundaries are always a little bit fuzzy, or are they consistent? Is that an issue?
That's a really good question because currently most of the sensor detection metric, they don't care about the boundaries because the bound is like they treat boundary and inside of the objects, some objects like equally. So most of these metric, they can't evaluate whether the prediction is sharp or not. This is issue and this is a thing I'm working on right now. Hopefully I can have yeah. So you raise a very interesting question. Hopefully we can have some new metrics for this, but it's not that maybe we can try boundary LU or some other matrix to evaluate the accuracy of the edge. But currently, no, the MAE cannot estimate the edge accuracy. Some other metrics still no.
It's interesting to think about the next part in the pipeline, right? You do saliency detection in order to use it for something, for something else. And maybe for those other applications down the line, then the boundary doesn't matter that much. You want to put the center point and like the general area where the interesting part is. So let's talk a little bit about the results. So except getting the bold numbers and getting an amazing improvement on previous methods, what have you observed on the results? So where did your method shine, and what limitations does it have?
The most interesting part of this network is that it can produce uncertainty estimation instead of single prediction. And with this uncertainty map produced, you can understand that the model may be overconfident along some area. And from my experience, especially from our work of the UCNet, the current uncertainty usually along object edges. If you just visualize the uncertainty map, you can observe that the uncertainty area mostly along object edges, and also it happens that it may also appear in object that is discussed while you prepare the ground truth, which is a less excellent area. So this is our prediction. And also the performance is good, but this is, I believe, is the most interesting part, that it can understand where I should not be that confident.
So it's really interesting, right? It makes sense to have more than one salient feature, and then maybe those other salient features are important as well for depending on the application, right? You sometimes want to get all those other candidates, the competition. What's the limitation? So when does it fail?
One time, as I mentioned just now, when we get the multiple ground truth, we use helic. But it happens. The ground truth may be noisy. Sometimes the generated multiple ground truth may not be that accurate, to be honest. And the edge it may not be accurate. Although we use CIF to refine the pseudo ground truth, but still it's not that accurate. So this is one limitation of our algorithm, because we generate the multiple ground truth for our task to make the latent variable reasonable, but still, because the ground truth is not that accurate, so the latent variable sometimes may not actually learn the uncertainty of the ground truth. So this is one limitation. Another limitation is that our current model actually is very simple. It's early fusion model, because usually when you have RGB image and depth, the best way is to do cross-model fusion, which means you can fuse the feature of RGB image and depth, feature of the depth. But currently, we simply concate RGB and depth in the input layer, which is early fusion model. And also because the depth is not that accurate, to be honest. Currently, for RGB-D sensor detection, the depth is from Kinect or from stereo. For stereo, usually the depth is kind of accurate, but for Kinect, the depth from Kinect is noisy. It's not, especially the edge, it's not well aligned with image. So that may be noisy in the depth maps. So simply when you concate the depth and input RGB image, you can introduce depth to network. So this is our next step of next plan to reduce the noise inside the depth, make the model more robust make the model more robust to the input noise.
Yeah, that's exactly where you want the accuracy, right? It goes back to the boundary issues, right? Right at the boundary, you have the misalignment of the depth and the RGB, and that's when you want to get it right, and that's where you don't have the data.
Yes.
Okay, so moving on to the conclusions and future work section of the paper. So how do you see the impact of the paper so far and future directions for novice PhD students that might be listening and want to explore this field? Where do you see the most potential going forward?
So I think, as I mentioned, the most beautiful part I loved about this paper is still the uncertainty estimation. But one aspect missing in this paper is how can we use the generated uncertainty map? Because we only show that you can get the uncertainty map, but we didn't mention how you can use the uncertainty map. Because once you have the uncertainty map, one way to use it is just for visualization. You know that the uncertain area should be like along object edges, but actually there's one direction of research which is difficult aware learning, which means when you have the uncertainty map, you can just feed this uncertainty map back to your network and make your model to generate more reasonable predictions, because this uncertainty map is just highlighted the hard pixels. When the network is uncertain about this area, which means this area is hard, it's difficult for the model to learn, we can define them as hard pixels. And yeah, similar to Foucault laws, you can use this one as hard samples, and this one can be feedback to your network, maybe as weights or maybe as mask. I'm not quite sure, but I think more direction or more direct, more research can be done in this area to use the uncertainty map instead of just for visualization.
So now for my favorite part of the podcast, I call it "What Did Reviewer 2 Say?" So yeah, please share some reviews you got for the paper when submitting it. CVPR is a tough crowd, so there's got to be some reviewers that had something to say.
Our initial review is 1, 2, 3. So it's one is strong accept, two is weak accept, and 3 is borderline. This is our initial rating. And after rebuttal is 3 strong accept. And so the 3 main focus is that he's maybe not quite familiar with a generative model. So he think, okay, it's only a generative model application. He don't know that we use generative model for uncertainty estimation. So this is really, and it's new. So that's why he gave us 3. He think, okay, because VE is used everywhere. You see, VE for post estimation, VE for object detection is everywhere. Why you still use VE in your framework? So this is his main concern. That's why he gave us 3. So we explained that we're not using VE as a typical way. We use VE in our task because we want to model the subjective nature of saliency. This is what we want to achieve. We want to make it like an uncertainty estimation tool instead of generating new samples. So this is the concept is totally different. So this is what we explained in the rebuttal, and then after rebuttal, he just changed his mind to a strong accept. And for the review 2, he gave us a weak accept. He just concerned about the performance. He think the performance. I don't know, maybe he's too concerned about the performance, but we just argue that performance is one aspect of doing research. You want your model to be good, and the best way to prove that your model is good is by performance. But another way is by explaining why your model is good, is by your model can inspire people. Right? It's not okay. I provide a very good model, and yeah, that's it. We want to show that our model can produce good performance at the same time. We want to inspire the fellow researchers that saliency detection can be done in this way. So this is typical different from the previous work. And then after this kind of rebuttal, he changed his rating to a strong accept. So we end up with 3 strong accept in the end.
Yeah, I really agree. It's not just about the ball numbers. I mean, the ball numbers are important, but you want to make a paper that has a good idea behind it and something that can inspire people and branch out into other fields and everything.
Yeah, for feature work, I think currently the most structural or most powerful tool is transformer. And I noticed some people using transformer in a generative neural network for pose estimation already. This morning I just read that paper. It's VIT transformer for pose estimation. So I'm thinking about maybe combine generative model and transformer, because transformer is powerful in feature embedding, and variety and VE is powerful in like extract the uncertainty of prediction. So I'm thinking about combine the transformer with VE framework for my task, and hopefully we'll have good results in the end. But yeah, whenever that's powerful tool, why not just use it?
Anything else you would like to add?
I want to talk about if there's female audience. I want to give them suggestion. If you are a mommy and you have your kids to raise, don't be afraid because you can. I'm a mom, yeah, and you can still do research, so that's fun.
Oh, that's so important, so inspiring. Yeah, you can be a parent and do good research.
Exactly, yes.
Great message. So that's it for UCNet, uncertainty inspired RGB-D saliency detection via conditional variational autoencoder. Thank you very much, Jing. Thank you for listening. That's it for this episode of Talking Papers. Please subscribe to the podcast feed on your favorite podcast app. All links are available in this episode description and on the Talking Papers website. If you would like to be a guest on the podcast, sponsor it, or just share your thoughts with us, feel free to email talking.papers.podcast@gmail.com. Be sure to tune in every week for the latest episodes, and until then, let your papers do the talking.